We are now going to learn how to predict the actual products of a double replacement reaction when all we are given are the reactants. Okay. We talked about the term soluble and insoluble. We learned how to use the solubility rules. We will be using solubility rules to predict the states of matter of the products in double replacement reactions. This is the only time now between now and the end of the chapter that we're going to refer back to states of matter. Okay, so you won't need to worry about states of matter again, except for double replacement reactions. The reason is because in a double replacement reaction, if a precipitate does not form, then it is not even considered a reaction. It means no reaction happens. So we must always predict the states of matter. So if you see a solid, then you know that something has actually occurred. Okay, so we'll show you as we go through some practice examples how that is. Okay, so again, we are going to work with two ionic compounds. In every double replacement reaction, the compounds are going to break apart or dissociate into their ions. They're going to mix up and they're going to repair up with a new partner, and we're going to end up with two new products. So every time we do a double replacement reaction, we will have exactly the same process. Once we get to the other reaction types, you have to think a little bit more. Okay, so that's why we're going to focus on these first. All right. So this is not correct, and we're going to talk about why, but I wanted to show you this just to kind of show you the general format of a double replacement reaction. So in a double replacement reaction, you will always start with your two ionic compounds. And essentially, we said that all that happens is that our ions are going to break up, and then our two positive ions, the one in the front, are going to trade places. So sodium is going to pair up with oxygen, and barium is going to pair up with chlorine. So in a simple world, we would simply chop them in half, rearrange them, and write the new formulas. But unfortunately, chemistry is not a simple world. In reality, you still have to follow the rules for the formula writing for ionic compounds. Let's take a look at why these formulas were correct. Okay, in all ionic compounds, the formula is determined by the ratio of charges. How many of each ion does it take for them to cancel each other out? With sodium and chlorine, because they are both +1 and -1, they cancel each other out. They have that net charge of 0. So it only takes one sodium to balance one chlorine. I'm not going to use the term balance because we're going to say balancing for coefficients. One sodium to cancel out the -1 charge of the chlorine. Okay, so that is why there are no subscripts written. It is a 1-to-1 ratio. When barium and oxygen combine, you have a +2 ion combining with a -2 ion. So again, +2 and -2 already cancel each other out, so it only takes one of each ion. Again, why there are no subscripts written is because one barium combines with one oxygen. But let's look at what that means when they recombine with a different ion. When sodium pairs up with oxygen, it is no longer a 1-to-1 ratio, because with sodium's +1 and oxygen's -2, they don't cancel out anymore. So in order to get these two to cancel out each other, we need 2 sodiums to cancel out the oxygen. So this is the new formula for our product. When barium combines with the chlorine ion, again, barium was +2 and Cl was -1. It takes 2 chlorines to cancel out the barium ion. So we're going to go through this process in much more detail, and I'm going to show you an easy way to figure out who pairs up with which. Okay, but notice that the subscripts on this side have nothing to do with the subscripts on the other side. The charges are what determine the subscripts, and the charges come from where? The periodic table. Okay, so what is here is not relevant for writing the formulas. You just need to look at the charges. There will be a case where we do need to look at formula, but we're going to handle that one last, and it has to do with our type 2s where we can't look it up on the periodic table. Okay, so let's go through these steps. So first of all, these are the steps we're going to use for writing, or the rules for writing. Number one, we're going to start by writing the ions with their charges for the reactants. Okay, so kind of like I did here, and you're welcome to use this method, but I'm going to show you another method that you can use as well. We will need to use subscripts only when we need to figure out the charge of a type 2. We'll go through that example. Okay, we're going to switch partners. Our cations are going to switch and pair up with the other anion. We're going to write our new correct formulas on the product side based on the net zero charge. Okay, do our charges cancel out? Once we have all the correct formulas, we are going to balance using coefficients. Okay, those are the numbers in front. We'll do this example again, we're including that. And last but not least, it's not included here. I added on the next slide. We will determine the states of matter of the product using the solubility rules. Okay, so is it aqueous or is it solid? In double replacement reactions, the reactants are always aqueous, so we don't have to indicate their states. You can just assume that they will always be aqueous, okay, meaning they'll be in their liquid form. All right, so let's work through this step by step, utilizing the technique that works for most students. So this is what you will see, and you will be asked to predict the products of the reaction. First of all, you have to identify which of the 5 types of reactions it is. Okay, right now we're only working with double replacement. How do we know, based on the reactants, that this is a double replacement reaction? Carter? We have 2 compounds. It's the only reaction type that starts with 2 compounds. So if you see 2 compounds, we are double replacement. Okay, first thing I'm going to do, and again, you're welcome to do this right above them, but some students, to help with the pairing, find it easier to do it to the side. I'm going to write my 4 ions. Has nothing to do with the subscripts. It simply comes from the periodic table. So Na, I'm going to do this to the side, is in group 1, so it's +1. Cl is in group 17, so it's -1. So there's my first compound broken into its ions. Now I'm going to do the same for this compound, broken into its ions, and I'm going to do it right below it because this is going to help us figure out the pairing. Barium is in group 2, so it's +2. Oxygen is in group 16, so it's -2. Okay, so first compound, second compound. Now they trade partners. Crisscross. Okay, this will tell you what they're going to pair up within the product side. Na is now going to go with O. However, notice that now it's no longer a 1-to-1 ratio because Na is +1 and O is -2. So I'm just going to do a little scratch work on the side here for those of you that still need this extra help. To get your charges to cancel, we need 2 NAs for every 1 oxygen. So that is where our new chemical formula comes in. 2 NAs for every 1 oxygen. Now that barium has combined with chlorine, barium is +2, Cl is -1. It takes 2 chlorines to pair up with 1 barium. So that is how we officially get the formulas. Those formulas are now set in stone. If you did this right, you will not change those subscripts. So our next step is we're going to balance the chemical equation using coefficients. So these are what we're going to write in front to get the numbers of atoms to work out. 1 sodium on the reactants, 2 on the products. So we're going to put a 2 in front here. Notice there are not lines drawn, okay? You're going to just use that space to fill in your coefficients. That gives us 2 chlorines on the reactants, and we already have 2 chlorines on the product, 1 barium on the reactant, 1 barium on the product, 1 oxygen, 1 oxygen, okay? If you go to balance and it is impossible to balance, that means you wrote one of your products wrong. Okay, so if you're balancing and nothing works out, you definitely did something wrong when you wrote your products. So go back and double check them. Okay, we can fill in ones if we'd like, but they are not required. And now the final step, and this must be done for every double replacement reaction to get full credit, you have to predict the state of matter of the product. So this is where we're going to use our solubility rules. So first, we're going to find oxygen on our solubility rules. This so happens the solubility table does not have oxygen in it, so I'm going to tell you this one. This one actually is a solid, okay? I will not give you any on the test that are not on the table. The second one, if we look up chlorine, it says all chlorides are soluble except AgCl, Hg2Cl2, and PbCl2. This is not one of the exceptions, so this is soluble. Remember, soluble is aqueous, insoluble is solid. This solid means a precipitate formed. So this was a successful double replacement reaction called a precipitation reaction. Okay, so here is your final balanced precipitation reaction. All right, we're going to do several more examples here to make sure you're secure. I know some of you probably are comfortable already, but practice makes perfect. So let's do some more. Okay, you can do this in your more examples section. Okay, I don't give a whole lot of space, but you can write down below where it says to do the question. Okay, so here is 4 different reactions. Again, they are all double replacements because they are all 2 compounds. All right, what is step 1 for the first one? What are we going to do? Don't necessarily read this up here. What are we going to do over here to the side? Break it up into its ions. Okay, so we're going to write each of these as their ions. AlCl3 has aluminum ions and chlorine ions. The charge of aluminum is +3 because it's 1 in that staircase. The charge of chlorine is -1. Notice I didn't pay any attention to this 3. I didn't need to because both of these are on the periodic table and we can determine the charges. That 3 came from this ratio. All right, now we have calcium and sulfur. Again, we can find both of these on the periodic table. Calcium's group 2, sulfur is group 16. What do we do next? What's our next step? Logan, what do you think we're going to do next? Yeah, we're way far away from that. How do we know what our products are? What do we need to do over here? Put them together. How? Are we going to put these 2 together and these 2 together? We're going to crisscross, right? Okay, we're going to crisscross. Now we know our new pairings. So aluminum is going to go with sulfur. Could I write sulfur and then aluminum? No, why not? You said no. Because what? You were right. Say it again. Because what comes first? Aluminum must come first. Why must aluminum come first? Because it's a positive ion, okay? Positive ions always get written first in your compounds. So that is why we can't put sulfur and then aluminum. So it always goes positive ion, negative ion. So because we know aluminum is pairing with sulfur, we now use these charges to figure out the subscripts. So Al plus 3, S minus 2. We're going to get to 6. So it's going to take 2 aluminum ions and 3 sulfur ions for that ionic compound to be stable. Our other product is the calcium ion, positive first, combining with the chlorine. And again, because calcium is +2 and Cl is -1, this time it's going to take 2 chlorines to balance out the 1 calcium. Erase this. All right, so we have predicted the products, but that's not the end. Now we need to balance with coefficients and predict the states of matter. 1 aluminum, 2 aluminums. So we're going to put the coefficient 2 in front there. 6 chlorines, 2 chlorines. So we're going to put a 3 there. 1 calcium, 3 calciums. So we're going to put a 3 there. 3 sulfur, 3 sulfur. Okay, now, if you had done this and you hadn't had that 3 there, and you're like, wait a minute, something's not right here. I can't get this to balance. That would say, hey, you did something wrong. Your formula's wrong. Okay, so go back and double check it. Final step, states of matter of the products. We have a sulfur. All sulfides are soluble, except, all sulfides are insoluble, except those of groups 1 and 2 and NH4-2S. Is aluminum in group 1 or 2? No. So therefore, it is insoluble. It is a solid. Calcium chloride. So chloride says all chlorides are soluble, except AgCl, Hg2Cl2, and PbCl2. This is not one of those 3, so it is a whiz. Did this reaction happen? Did a reaction occur here? Yes. How do we know, Kara? Because a precipitate was formed. Here's our precipitate. So this one does, in fact, react. Okay. Next one. We're moving a little quicker through these. Okay, so here we have some polyatomic ions. It doesn't affect anything because polyatomic ions are groups that have charges. So we're just going to treat them as groups. So this time we split aluminum and bromine in half. Aluminum's charge is +3, bromine is -1. This one is made of 2 polyatomic ions, so you will look them up. NH4 has a +1 charge. We haven't used that one in a while. PO4 has a -3 charge. We still crisscross. Crisscross. Aluminum will now pair up with PO4. Do the charges cancel? Yes, so it is a 1-to-1 ratio. Al, PO4. Does NH4 and Br cancel? Yes, so it's a 1-to-1 ratio. Again, NH4 is the positive one, so this time our polyatomic ion is in front. And then Br. Now we balance. 1Al, 1Al, 3 bromines, 3 bromines. 3 NH4 groups. This 4 is inside the parentheses, so it doesn't count as a number. 3 NH4 groups, 3 NH4 groups, 1 PO4 group, 1 PO4. Okay, last step, predict the states of matter of the products. So PO4 says all phosphates are insoluble except those of group 1 and NH4PO4. Is this in group 1 or is it NH4? No, so it is insoluble, solid. NH4Br. All bromides are soluble except AgBr, Hg2Br2, and HgBr2. This is not one of them, so it is soluble. Did a reaction occur? Yes, because a solid was produced. Okay, try this next one on your own. All right, I will go over that particular example tomorrow, okay, just as a refresher, but let's go ahead and look at this last one. Okay, so same process, nothing different, still a double replacement reaction. It's just that we're going to find that we need a little bit more information. I'm going to rewrite it up higher just because so low on the board. Hold on. Which one? The old one? Yes, if you can. Okay. Let me just mute this because it's going to be easier. Okay, so the last example is Cu2SO4 plus SRNO3. All right, so we want to predict the products. Again, we know it's a double replacement reaction because we have compound plus compound, same process. So we have copper and sulfate. We're going to go to the periodic table. We're going to find copper, write the charge of its ions. Uh-oh. Copper is a transition metal, which means we can't find the charge from the periodic table. In chapter 9, how did we use our chemical formula to figure out the charge of that ion? Anyone remember? Kara? The second ion. Yes. Remember that the second ion, the anion, we always know the charge for. So SO4, we know is -2. If this has a -2 charge and it takes 2 copper ions to match up with that -1, -2 charge, what is the charge on a single copper? Nyla? You're right. Don't doubt yourself. 1. Yes. So each of these is +1 to cancel out that -2. So the charge of a single copper ion in this case is +1. Okay, so when you cannot find the charge on the periodic table, that is the only time you need to think about the subscripts in the problem because they're going to help you find the charge. All right, so now we have the charges of these 2 ions. Going to do the same here, strontium and nitrate. Strontium is in group 2, so we do know that charge. Nitrate is the polyatomic ion with a -1. Still go through the crisscross. Copper is going to combine with our nitrate, +1 -1. So it is a 1-to-1 ratio. Strontium is going to combine with SO4. They already cancel. So again, it's a 1-to-1 ratio. balance it. You got 2 here. So we're going to put a 2 there. We have 1 SO4, 1 SO4, 1 strontium, 1 strontium, 2 nitrates, 2 nitrates. Okay, states of matter for the product. Nitrates is easy. All nitrates are soluble. Thank you. Sulfate. All sulfates are soluble except CaSO4, SrSO4. So this one is an exception. It is insoluble. So you have a reaction. Yes. The example you did on your little sheet there, you should not have had a precipitate, so we'll talk about that tomorrow. Okay. We got 4 minutes. I might as well go over this one. All right, we'll go over this example. All right, so we had, this was the one you just did on your slip. So you had BeNO3 plus K2SO4, and you were predicting your products. Beryllium ion, Be is group 2, nitrate ion, -1. Potassium ion, group 1, sulfate ion. Okay, crisscross. Again, this time your charges are going to cancel out in each direction, so they're both 1-to-1 ratios. So we have BeSO4 and KNO3. It doesn't matter if I had done KNO3 and then BeSO4. Okay, those are interchangeable as long as you have them paired up correctly. When we check the solubility rules for these, they are both AQ. If you have a situation where they are both AQ, no reaction happens. You still need to go through the entire process. You still need to indicate that there are 2 aqueous, but in reality, no reaction happens because everything just remains free-floating ions. The lab that we do coming up is going to have this situation where you have to decide where a reaction happens or not based on the precipitate. Okay, so the only difference is that nothing really happens even though you still